Hi all. In this video, we will be talking about how do we create standalone EKS Anywhere clusters. Before we go there, let's also do a quick recap that we already have EKS Anywhere admin machine, which was deployed using Terraform. It runs the EKS Anywhere software. We also have the OS template for our EKS Anywhere nodes, which has been customized. It's a Ubuntu OS template, which has been customized, created and customized. And we also have a base YAML, which will be used in the cluster creation process. This YAML is a set of resource requirements for our EKS Anywhere cluster, right? Like the machine configurations of the etcd nodes, control plane nodes, and the worker nodes, along with the size and configuration and everything else. So let's move ahead. I'll do a quick visual in terms of the cluster creation process. Note that there is for ease of deployment, we have wrapped the AWS suggested commands into a shell script so that we can execute just one shell script, and then it will basically take some input in terms of the name of the cluster, the Kubernetes version being created and all that, and finally run the cluster creation command, ekctl anywhere cluster create. So this is the shell script that is already loaded here. We execute the script. It generates a YAML for the intended cluster with the size and configuration mentioned in this YAML. This YAML is basically supplied to a Bootstrap cluster that runs as a Docker container on this Terraform machine or the admin machine. And once this Bootstrap cluster comes up, it takes these YAML files and then communicates to vSphere to provision these virtual machines. Basically, we will observe around 7 virtual machines as a part of this template, which is 3 etcd, 2 control, and 2 worker nodes. Actually, you could change the base YAML to increase the size of that cluster configuration in terms of the number of virtual machines, for different roles. For now, we are doing this exercise and demos with 3 etcd, 2 control, and 2 worker. Also note that the kind cluster basically runs cluster API pods as a part of the EKS Anywhere bootstrapping, and those cluster API pods will be communicating with vSphere. Once the cluster is fully created, all these resource definitions in terms of the machine configurations and all that, instead of then this particular bootstrap cluster has to be deleted. So once this cluster is created, but before this gets deleted, all these resource configurations are moved into a namespace here on the target cluster, such that all the resource definitions are actually placed as CRDs inside of that namespace, and the cluster API pods finally get moved from here and they get reinstated in this namespace. Along with that, you will also see a EKS controller will be running in a namespace here. And I'll talk more about this when you actually look at it from practicality standpoint, why all this circus happens here, and the reason for all this kind of movement of cluster API pods and the resource CRDs and all that. Actually, we'll see all of that actually. Now, if you've understood this visual, you can also understand that you can simply do parallel execution of the script for creating multiple clusters. It's not a sequential one. Every time you execute this script for creating a new cluster, a bootstrap cluster gets created, and that process that I just spoke to you about is kind of done to create a number of workload clusters. So now, if you understood this high-level overview of what's happening, let's move to my Ubuntu machine here. Just to kind of cite an overview, I'll just help you with that base YAML template that we were talking about, and this is already placed when you had created this or when we had created this admin machine with the help of Terraform. So this is already there as a part of the Git clone from the GitHub repository. So we just need to edit it, as I spoke in the previous video, for our specific vSphere environment, like the vSphere endpoint name, the data center name, and all that. So this is now the base template that I have. The only changes that I will require is, to replacing this term with the actual cluster name. Then if there is since this is a standalone workload cluster, the management cluster name and the workload cluster name will be the same. The version of Kubernetes that needs to be changed and all that. So all that we will do it through a script actually. So if if you understand this, the process of actually creating the cluster is quite simple. There's a script which is actually placed here, create EKS Anywhere cluster. This is also there or loaded as a part of the Terraform installation process for EKS admin machine. Once we run this script, you can see that it will ask for the workload cluster name. So let's give it EKSA C4 EKSA1. You could give it anything, but just make sure that since this is a standalone cluster, you got to give the management cluster name and the workload cluster name as the same. That's the only requirement here. We have to provide the static IP for the API server that will run on the control plane nodes as a floating IP. So I'll give it, let's say, a static IP. This has to be excluded from the DHCP pool. It appears as a floating IP that is managed through Cube API, which runs on the control plane nodes, facilitating the API server access. So once we have put in this IP address, I just insert, I want to run 1.22 so that it will change all the occurrences of 1.21 in my base YAML template to 1.22. Okay. Now, as soon as I execute this process, what follows is a set of validations by connecting to the vSphere through the through the credentials. The credentials are already kind of there in the profile of the EKSA admin machine. So you can see that the validations have started. If my YAML template was misconstructed, this would actually exit with an error. Right now it looks to be perfect. So it's gone ahead, and you can see that the first thing that it does is it creates a Bootstrap cluster. As I said, the Bootstrap cluster is a temporary one to facilitate the provisioning of the virtual machines by communicating with vSphere. So let's look at this Bootstrap cluster a little more in detail. So I'm going to open a parallel session here to the same admin machine, and we can see if I instruct the command docker ps, you can see that there are two Docker containers that have been spun up. The one of interest is this particular container. This is the Bootstrap kind cluster, and inside of that you can see that there is a EKS distro running, and this EKS distro will basically facilitate all the build tooling and everything required for EKS Anywhere and the cluster API to communicate with vSphere. So basically, if I just exec into this particular container, you will see what's going to happen here is let's just exec into it. So I'm right now doing an exec into the Bootstrap cluster via this Docker container. Oh, sorry. Okay. Yeah. So let's do this. Okay. So right now I am inside of that Bootstrap. So we can, since this is a kind cluster, kubectl is already there as a part of the whole, bootstrapping effort. I can simply say get pods -a, and you can see as of now, the default components of Kubernetes are just loaded. There is nothing specific to EKS Anywhere as of now created on this Bootstrap cluster. You can see in parallel the cluster execution script here. You can see that what's happening is the Bootstrap cluster has been created, and the cluster API resources or providers are being put onto the Bootstrap cluster. And this whole thing actually takes about 15 to 20 minutes, and we'll observe certain things as we steer along that process. So let's repeat this command to see what has been done. You can see after a few minutes, there are some new pods coming up inside of the Docker container Bootstrap cluster. These are the cluster API pods that I was talking about, and you can see they are in the process of running or container creating. Now, once you get these pods into the Bootstrap cluster, it is the cluster API pods that are actually going to take that YAML template of the cluster requirement here, okay, and then basically it will actually talk to vSphere. So let's see if the pods are already there. You can see that all the pods are back into action. They're all in running status. And you can also observe a few more details like the logs that are being generated. So let's just look at, okay, before we get onto the logs, let's also look at what CRDs or custom resource definitions have been created as a part of the Bootstrap cluster creation. So kubectl get CRDs -a, and you can see the ones of interest are here. You can see that these are all the resource requirements in the YAML that was supplied for the cluster creation process, and they have been supplied and translated into these CRDs. vSphere machine templates, vSphere VMs, then the vSphere cluster template and things like that, right? Also, all of these vSphere machines included. So all of these basically now are CRDs, and these then become a sort of resource request to the vSphere. Actually, we'll actually look at these CRDs in a slightly greater detail, but for now, understand that the resource requirement has gone to vSphere. Now, if I look into my vSphere environment, okay, you can see that already 3 machines have started. They have started to create here. These are the 3 etcd nodes. Totally, we will have a set of 7 machines. So the first 3 machines have already come up. In the cluster creation script process, I should be seeing that we are past the new Bootstrap cluster. The cluster API has been already deployed on the Bootstrap cluster, and now the cluster API has communicated with vSphere to create the new workload cluster. And as a part of that, you could see in the vSphere that these particular 3 machines have come up. Now, point is that as time progresses, you will see all the 7 machines come up, and you can see the 4th one is also coming up. This is the control plane node. Let's just wait for a minute before all the 7 machines are created, and we'll then observe what is the process actually, how does it take shape. Till then, we can also look at these CRDs that I was talking about, so that you understand what are the type of resource requests that have gone into from the cluster API pods into the vSphere. So let's examine one of them, kubectl get get this particular CRD. Let's say that. Okay, so you can see that if I was to describe this CRD type, I am seeing 1, 2, 3, 4, right? So these are specific instances of the node request. You can see that 1, 3 etcd and 1 of the control plane nodes. So these have gone as a set of requirements to vSphere. Let's also look at this particular CRD. Okay, kubectl get -a. Here you can see that this is all the set of requirements that will go as the resource request. So the MD0 is the worker plane definition, the etcd, and then the control plane definition. I mean, we can get into the, by describing this CRD, and you will see that the same YAML requirements in terms of resources and all that will be a part of this particular definition as well, actually. So I hope you understand what is a CRD, how does the cluster API basically invoke the YAML and put resource requests to vSphere to create the virtual machines required. We are still a little away from, okay, now 7 machines have been created, or the 7th one is being created. Now, if you see this, you will observe that our cluster will have these particular 7 machines, but the etcd machines will not bear any kubelet, which means that when we issue the command kubectl get nodes, we will only see these 2 control plane and these 2 worker plane nodes. We will not see the etcd nodes that we can observe here in the vSphere. Let's go back to our cluster, and you can see that it's still in the process of creating. We'll just wait for a few minutes till this process is complete, and I'll tell you what happens in the interim. We can also see now that it's the workload cluster has been created, and post the creation of the cluster, EKS Anywhere has a set of default CNI and default storage class, which I'll talk about. But the CNI and the CSI are being provisioned on the workload cluster. The CNI is going to be Cilium, and the default storage class, because it's vSphere, It's based on vSphere CSI. Now we are not limited to only using the default CNI Cilium and the default CSI of vSphere. We can bring in our own CNIs and CSIs. Like in this Saga series, we will be bringing in Dell CSI, for various storage arrays and things like that, so that you can derive your persistent workloads or run your persistent workloads on those CSIs. Also note that on that particular target cluster, a EKSA namespace is being created, and on that namespace, like how on the Bootstrap cluster, cluster API was being provisioned, now cluster API is being installed on the workload cluster actually. And then what will happen is from this Bootstrap cluster to this workload cluster, those cluster API pods will be shifted actually. And as a part of that shift, it will say management cluster capabilities moving. Those CRDs also that we see, these ones, will be also shifted or copied over to the target workload cluster. Why it happens, I'll explain to you in a little more detail so that you understand the relevance of this entire process actually. But as of now, you can understand that these are the CRDs that are of primary importance. And in terms of the pods, these are the cluster API pods that we are talking about, CAPI and CAPI, right? Let's look at where we are with the entire process of cluster creation. Still going on, so we'll wait for it. So we can now note that the statement of moving cluster management from Bootstrap to workload cluster. This is happening or happened, and then some of the custom components, the CRD and the controller is being performed on workload cluster. So as I said earlier, there is a controller called as EKSA controller, and I'll tell you the functionality on the role of that. For now, understand that those CRDs that we were actually observing here. Let's see this. Okay, by the time I could actually execute the commands, the Bootstrap cluster has been deleted, you can see. So this kind of validates the fact that it was a temporary Bootstrap cluster, and the CRDs that we were seeing and the pods of cluster API, all that is gone, right? Because the cluster itself, the Bootstrap cluster and the Docker container has been terminated, which means that now I can actually go and inspect. You can see here, the whole process is complete. The cluster has been created. Now the point is, how do I access this cluster, right? And I'll show you what it meant by transferring of those management capabilities onto the target cluster actually. Now, as a part of the cluster creation process, not by virtue of my script or the script that I've written, as a part of the EKS Anywhere cluster create command itself, a directory is created by default by EKS Anywhere, and it is named, it is always placed inside of, the home directory, and this directory is named exactly to the name of the cluster being created. And inside of that, you will see the kube config generated automatically for the target cluster. The YAML that was actually used to create the cluster is also here. Okay, so it creates that safe copy. Plus the SSH keys, the private and the public keys are also here. Now at this point of time, I can simply point my kubectl, the context and the kube config reference to this file, and I can start accessing the cluster in terms of the kubectl. So in order to do so, instead of doing the whole thing manually, what we can do is just use a handy script that I've created here. It's already there as a part of the whole admin machine creation. So it's called as switch cluster. So create cluster, switch cluster. Switch cluster would basically set the kubectl context so that you can operate with this particular cluster. So let's give it the name as the input. Okay, the moment we do this, we can start engaging with the cluster via kubectl. Let's do this and see if I can access the cluster. So now you can see that the 4 nodes, the 2 control and the 2 worker nodes are already in play. I can retrieve the information. I have kubectl access, which means that I should be able to start deploying my workloads, applications, and whatnot actually, right? Let's also see kubectl get SC. You can see that the standard default storage class is based on CSI VMware, okay? And what now we are doing is, earlier we had inspected the CRDs and the cluster API pods and everything basically on the Bootstrap cluster by logging into that Docker container. Let's look at now if those CRDs and the cluster API pods have in fact moved or transferred, to this particular cluster. So if I just list the pods, you can see that the cluster API pods are running here, right? The CapI and the CapV. You can see this. Plus, you can also see that there is a EKS controller which is actually running here. Now, I will talk about the role of these things as to why did they move on this standalone workload cluster. Okay. Now, point is that once the cluster is created, obviously as a lifecycle management, you would like to upgrade the cluster in terms of the resource configuration, the count of nodes, or the version of Kubernetes running and things like that. You can do that in several different ways. One of the ways is actually to change the YAML file. So I get into C4, that cluster directory, okay? And I can simply edit the YAML file from here, okay? Sorry about this. Okay, so I can simply edit the YAML file here by changing whatever I want to in terms of the resource requirement or the count of nodes or whatever. And then I can simply issue the command EKS CTL Anywhere upgrade cluster, and just give the file name of this updated one. I'm not going to do that here. So this is one way of doing it actually. Okay, so the other way of doing it is basically using the kubectl itself. So this is where the management, when we say that management cluster capabilities or management capabilities, it is nothing but the combination of the EKSA controller and the cluster API pods. Because if once I say kubectl get clusters or cluster, you can see that this kubectl is actually talking to the Kubernetes API server, and it is trying to retrieve the resource of the kind cluster. Now this is a CRD running in the default namespace. So, and it is actually bringing up this particular name as an output, which means that there is something of, something in that particular CRD that is of interest, right? So if I just describe cluster C4 EKSA, you can see it's nothing but our YAML template, a snippet of our YAML template, which was actually put in play to create the cluster itself, right? And I can see the count and everything here. Now, understand this. I'm getting this from the output of this particular, command. kubectl get cluster is basically retrieving a CRD information. And that CRD, if it was not present or the management capabilities were not moved from the Bootstrap cluster to the target workload cluster, I would have never fetched this information, right? Because the CRD would have never existed then on the standalone workload cluster. If I'm able to get this CRD, which means I should be also able to edit this CRD. What happens if I edit this CRD? So if I edit this CRD, I'm actually changing the size and configuration of my cluster. And that gets watched by kubectl get pods minus in EKSA system. So any change request to the CRDs, which is the cluster or the vSphere machine configs and whatever that makes up the cluster, those requests are actually watched by this controller manager. This is the EKSA control manager running in the namespace of EKSA system. Okay. Once this change request, let's say change comes in by editing this particular, CRD, EKSA controller then talks to the cluster API pods. Okay, so you could see that the cluster API pods were also running there. You get pods. sorry. Okay, so EKSA controller manager will receive that, or will actually observe that there is a change in the cluster definition. It will communicate the requirement or change to the cluster API components. Cluster API components will talk back to vSphere. Okay, vSphere will change the machine configurations or add in a new machine and all that. And then what will happen is, as a part of that overall change workflow, you will see that the cluster would have actually moved on to a desired state as specified in the new edited YAML of that particular thing. And we can see this, I'll show you this particular thing, and that kind of will establish the fact as to what is the importance of when we say management cluster capabilities, basically, right? The other point is that, while we are doing, or while we will actually do this particular edits through kubectl instead of EKS Anywhere, upgrade command, this same process can be done through a GitOps pipeline also, where you are storing your cluster templates, in a GitLab repository or a GitHub repository, and then through a GitOps mechanism or any other standard pipeline CI/CD mechanism, you invoke through the Kubernetes API change through applying a change of that YAML file. Okay, so think of it that your EKSA controller, which is actually an API listener of sorts, request listener, can listen to these change requests for the cluster configuration from anywhere, either through an API call coming through kubectl or through EKSCTL, or it could be a third-party software which can actually do an API call if authenticated rightly. And all they need to do is change the provide a new resource specification for the cluster. The EKSA controller will listen to that, communicate with the cluster API. Cluster API talks to vSphere. vSphere provisions the changes, and then the loop is completed by the new nodes or the new configurations getting inserted into the cluster. Instead of talking about it more, let me just show you how it happens. Note that while I'm on this machine, EKS Anywhere admin machine, you could do this from any other machine from which you have access to this cluster. Now I can create a kube config like a regular business, or I can create an OIDC SSO based login into this cluster. So from any machine that you have access to this cluster, kubectl, or from third-party systems, like I said, you can simply edit the cluster. Okay, and you can see I'm going to edit the cluster here. Let's do, for example, I'm going to increase the worker node count to 3. Okay. Instead of doing VI, which I don't like VI as such, but let's use cube editor, okay, equal to nano, and kubectl edit cluster. Okay, so if I do this editing of cluster, like I said, I'm going to increase the resource count or the VM count for my worker nodes to 4. Okay, or let's do a simple one, 3, so that we can finish this quickly. As soon as I apply this, okay, you can see that this is the CRD that got edited. And once this has been edited, if I look at get nodes, okay, right now, even now there are 4 nodes, 2 control and 2 worker. I have asked for a change for the worker node count. So let's just see if that will happen. You can see that the 5th or the 3rd worker node, which is not ready as of now, has been already created. So you can see that it was so quick that the moment we issued a change request to the cluster configuration, the entire process of the EKSA controller talking to cluster pod talking to vSphere. We can see here also that there are 3 worker nodes now instead of 2. So now there are a total of 8 machines as opposed to 7 machines. And let's go here, clear, okay, kubectl get nodes. And you can see this will take a bit of time, maybe 3 minutes or whatever, till the whole node is readied and it is a part of the entire reconciliation that happens at a cluster level. But I hope you understand the entire cluster creation process as such that we explained here in terms of how the script was used. So look at it from that perspective. The entire cluster creation process only took about one script and 15 to 20 minutes, whatever it was. And the process around this whole Bootstrap, the cluster creation, movement of Bootstrap, why it happens and everything, I've kind of shown it to you from a practical perspective here. I don't have right now GitOps toolkit installed, otherwise I would have showed you a similar thing from changing configurations in my GitLab. Like I would take the same YAML file from here, this one, okay? I would take this YAML and I will commit it to my GitLab and integrated it through a GitOps controller like Argo or Flux or Fleet, whatever. And then once I change the YAML in that GitLab, obviously GitOps controller will communicate with my Kube API server. Kube API server will direct the changes. The EKS controller will listen to it. It will communicate to cluster API pods, cluster API to vSphere, and back to creating resources, changing resources, and reconciliation. So that's a wrap on the standalone workload cluster. In summary, it's a embedded functionality of running the workloads, your applications like regular applications and pods and everything. Plus, it also instills or embeds the management capabilities or the self-management capabilities through cluster API residing on the same cluster. So thank you. Hope this benefit or you were benefited from this knowledge. Thank you. So now that our cluster is fully ready, I've shown you the various interactions in terms of the cluster creation process and everything all put together. What we can now do is, deploy a sample workload. Not that it will make a lot of difference, but just to kind of close the loop, we will quickly deploy one of the sample workloads. It's already placed in one of the Hello World directories here. You can see this deployment.yaml, and you can see that the Hello World application has been created. Let's get the pods. You can see 2 instances. Now the point is that you can start using this as a production cluster. I mean, it's production ready, and you can simply keep increasing and doing multi-tenancy on the cluster by namespaces and whatnot. And as long as you have the underlying resource capacity, you can keep deploying your applications here, right? And from a cluster management standpoint, in terms of scaling and whatnot, I've already demonstrated how easily we can actually scale this cluster. You can also apply cluster autoscaler, to actually do autoscaling on the cluster in tandem with the underlying, infrastructure as a service provider. So all that can be done, whether it's at a pod level, autoscaling, or at a cluster level autoscaling. Note that when you are doing GitOps style cluster scaling and all that, it's more semi-automatic as opposed to full automatic. But if you do auto scaling on the cluster, through the cluster autoscaler project, many different possibilities can be achieved actually. So that brings us to the close of this scenario where we understood what is a standalone workload topology, workload cluster topology. And in the next video and blog, we will understand the workloads which are managed through a dedicated management cluster. Note that in the next example, I will be using the same cluster. I'm not going to repeat the entire exercise because, although this is a standalone workload cluster, if I just delete the Hello World application here, you can simply delete this, delete, and clear. And I promise to myself that I will not deploy any production applications, end user applications on this cluster. This might as well become my management cluster, right? I might decide to, on a need basis, I can put shared services applications, like I said, multi-cluster applications, like Cube apps or Argo CD and things like that, as long as the resource capacities permit on this management cluster. But preferably, if I convert the role of this, from a terminology standpoint to a management cluster, I will cease to deploy any end user applications on this. That's the primary importance. So in the next video, we will use this particular cluster as a reference for a management cluster instead of a standalone workload cluster. And then from there on, we will actually start to discuss the workload clusters that will be managed via this particular management cluster, C4 EKSA. Thanks a lot.